If you wanted to actually do an exact simulation, it would take 10 to the 48 classical bits. Using qubits, you could do it for only 160 qubits.
Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Jeff Welser, Vice President of Exploratory Science and University Partnerships at IBM Research. So Jeff, we've been hearing a lot about quantum computing lately. Could you give us a quick overview of what quantum computing is?
Sure, happy to do so. Thanks for having me, Lisa. Quantum computing really tries to take advantage of quantum mechanics to do computation in a completely different way. If you think about a normal computer, we are used to the idea of using bits, where a bit can either be a 1 or a 0 to represent information. And by doing that and making very large numbers of bits, like on our disks and on our phones and in our computers, we're able to manipulate information at very large scales and do obviously a lot of amazing computation. In a quantum computer, the basic unit you're using for storing information is something called a qubit or quantum bit. And a qubit can also be a 1 or 0, but because it's actually represented by a quantum state, it can use quantum mechanics to be a superposition of a 1 and a 0 at the same time, or a probability of being a 1 or a 0 at the same time. So in a sense, then you can actually represent a vastly larger number of states at once. And in the simplest terms, what that means is when you're doing computations, you can test all those states in sort of one step versus having to actually test every different combination individually. So the power comes from this ability to represent large states if you can actually apply it to the problem at hand.
So how does one go about making these qubits, and how is nanotechnology connected?
So a qubit needs to be something that can represent a superposition of states between a 1 and a 0, as I mentioned. So you have to think about a device that can create a quantum state. The one that's probably most popular, and we're utilizing at IBM as well as other companies, is a superconducting Josephson junction oscillator. So basically, this is just a superconducting oscillator. It has to operate at very low temperatures that can be either in its lowest state, which would be a 0, or it can be in its first excited state, which would be a 1, or it can be a superposition of those two states. So the idea is to fabricate those devices so that they're very clean interfaces, very isolated from the world in very low temperatures, as well as electrically isolated. And that requires a lot of work on the materials that go into those structures. It all has to operate at millikelvin temperatures, literally 15 millikelvin or so 15 thousandths of a degree above absolute zero. That's about 200 times colder than space, which is about 2 to 3 Kelvin. So very, very punishing conditions. So getting materials that can actually do that is a huge challenge. And there's other places where nanotechnology could be used. Other ways of doing qubits are entrapped ions, where you literally take an ion and you isolate it in a magnetic and optical sometimes chamber, and then manipulate that ion to be in either a spin up or a spin down state, for example. And that could be your 1 and your 0 for the quantum state. Or manipulating individual photons as well and the spin of those photons. All of these require us to actually manipulate matter at the nanoscale.
So you talked about the challenge of having materials that can operate at these very low temperatures. Can you discuss some of the other unique challenges for developing these types of qubits?
Yeah, so on the superconducting side in particular, you need to maintain this isolation, because if anything disturbs a qubit, it will actually automatically switch to either a 1 or a 0. It will lose its superposition. So obviously I talked about the temperature and the electrical isolation, but the materials themselves make a big difference. The interfaces you create in forming your junctions, your Josephson junctions, need to be extremely precise. They can have no variation at the atomic level. You have to think very carefully about any impurities that are actually being put into those devices that may cause some sort of electrical charge to come off that would actually cause these qubit to decohere. And there's also things we don't even understand entirely yet. What about the structure and the way you lay out the actual structure in the material could affect how long that qubit can last? That's probably the biggest challenge for superconducting qubits is their lifetime. Right now, they can last maybe 100 microseconds or so, which sounds very short, but we're very proud of that time. That's a very long time for a superconducting qubit. But we'd like that to be longer, obviously. So how do you continue to find ways to make the materials more amenable to being able to keep that state for a long period of time?
So how do they compare to the normal computer that the laptop that someone might use. Is a quantum computer going to replace my laptop?
Yeah, so quantum computers definitely will not replace laptops or even mainstream supercomputers today, high performance computers. They will, however, allow us to do certain problems that you can't do any other way. And these are problems such as simulating a molecule, for example. So today we do use some of our very large high performance computers for doing molecular simulations, but it turns out you can only simulate a very small number of atoms in a molecule if you want to do it exactly. Otherwise, we use approximations and other tricks to be able to estimate what the actual energy levels are in that molecule. And a good example is the molecule, let's say caffeine, which is something I think all of us like a lot. It's not a particularly large molecule. It's got about 95 electrons in it. But if you wanted to actually do an exact simulation of that molecule, the molecule of caffeine, it would take 10 to the 48 bits, classical bits on a system. And for reference, the planet Earth has about 10 to the 50 atoms in it. So you're talking about using 1% of all the atoms in the planet Earth to go build this. Obviously, you'll never do that. It's not possible. But using qubits, you could do it for only 160 qubits. So that's something that's actually quite feasible to reach in a short period of time. And that's because of the large number of states that they can represent. So for problems like material simulation, things like optimization problems, similar problems to say like the traveling salesman problem, or other types of search and factorization algorithms, there are certain problems that map on quantum computers that can't be done any other way.
So how do you view the future of quantum computing? I mean, you mentioned some of these specific applications where this approach is going to be able to get to answers that we can't do with even a supercomputer. But where do you see the future of quantum computing?
Yeah, I think that right now what we're really doing is we're creating an ecosystem to try and have people start to utilize even the crude quantum computers we have today, and getting people in the sciences and who are in engineering fields to start to play with them and try to apply them to the problems they're working on now so we can understand exactly where they're going to best fit. Starting in May of 2016, IBM put a 5-qubit quantum computer out on the cloud that anyone is free to access. If you look up IBM Q on your browser, you can get access to the system. Now we actually have systems that go up to 17 qubits for public use, as well as up to 53 qubits for some of our partners. But the point of it is that we want people to just go use these systems and actually start to experiment with them. We have something called KISS Kit, which is the Quantum Information Software Design Kit that helps people actually write programs as well. And we're finding people are starting to build up in GitHubs and Jupyter Notebooks applications for using quantum computers in chemistry or even playing games. Someone put a quantum battleship game out on the cloud to use. And we really do encourage particularly students and people who are in the science and engineering to start playing with these systems, because I think as we do that, we're going to discover rapidly where the applications will really have the most advantage for quantum systems.
So do you have any advice for students who might be interested in going into a field like quantum computing?
I think that the most important thing, if you're interested in quantum computing, beyond obviously just going and playing with the systems now to learn about them, is to make sure you're getting a really good background in some base level quantum mechanics. But after that, rapidly thinking about an application space where you want to use it is probably more critical. Over time, we'll find ways to make sort of quantum weirdness of programming it more and more invisible, so that you'll be able to program in Python and higher level languages. But understanding how you map something onto a quantum system requires good knowledge of course, the problem that you're trying to solve, but also of statistics and linear algebra and matrices, because those are all things that are very applicable to how a quantum system actually goes and tries to solve the problem.
Well, thank you, Jeff, for really breaking down quantum computing for us and sharing your time today. Do you have any closing thoughts for our listeners?
I just want to emphasize again the importance of starting to familiarize yourself with these systems. I think that while quantum computing is not going to replace our standard computing, it's an opportunity right now that is really very similar to what we've seen in, say, AI over the past 10 or 20 years, where there's going to be a huge growth in applications and utilization of it. So it's one where if you're thinking in your early grad school where you're going to go, I would highly encourage people to consider thinking about how that might fit into where they go.